Okay, let's dive into this. We all feel it, right? Every single second of our lives, time just moves forward. But have you ever really stopped to ask why? I mean, why is the past set in stone and the future this big unknown? It seems like the most obvious thing in the world, but it turns out to be one of the deepest, most profound mysteries in all of physics. Think about it like this. You watch a glass fall off a table and shatter into 1,000 pieces. We've all seen it. But have you ever seen those 1,000 pieces suddenly leap off the floor and reassemble themselves back into a perfect glass? Of course not. But why not?
Or an egg, you crack it, you whisk it, and boom, scrambled eggs. But no matter how hard you try to stir it backwards, you're never, ever going to turn that back into a perfect yolk and a separate white.
Same with your morning coffee. You pour in a splash of milk, it swirls around, and everything becomes this one uniform, delicious color. But that milk and coffee will never just spontaneously separate themselves back out again.
And you know, this isn't just about stuff out there in the world. It's about us, inside our own heads. We have vivid memories of what happened yesterday, but we have absolutely no memories of what's going to happen tomorrow. This fundamental one-way street of experience. That's what we call the arrow of time.
So all of this leads us to this massive conflict, right at the very heart of physics. It's this deep contradiction between the fundamental laws that are supposed to govern reality and the reality that we actually experience. People call it the time puzzle.
And here's the puzzle right here on one slide. All of our fundamental laws of physics, we're talking everything from Newton to Einstein to quantum mechanics, they honestly don't care which way time flows. They work just as perfectly forwards as they do backwards. I mean, if you saw a video of planets orbiting the sun and played it in reverse, it would still look perfectly normal, physically speaking. But the world we actually live in, our world is blatantly, undeniably irreversible. So what gives? Where does this one-way street actually come from?
Well, the first huge clue didn't come from some brand new, complicated law. It came from something much, much simpler. The brilliant physicist Ludwig Boltzmann had this incredible realization. It's all just counting. Now, to get this, we need to understand a really key distinction. There's the macro state. That's the big picture stuff we can actually see and measure, like the temperature or the pressure in a room. And then there's the micro state. That is the impossibly detailed, hidden information about every single particle, exactly where it is and exactly where it's going. We only ever see the macro state.
Okay, so imagine a box and all the gas molecules inside it are crammed into just the left-hand side. There are actually very few microstates that you can arrange all those particles to look like that. Physicists have a name for this kind of orderly, low-probability setup. They call it low entropy. You can think of entropy as basically a measure of disorder or randomness.
But what happens if you let that gas expand? Well, it fills the whole box, right? But why? It's not because of some magical force pushing it, it's simply because there are countless more ways, just astronomically more microstates, where the molecules are spread out all over the place. The system isn't trying to be messy, it's just wandering through all the possible arrangements it could be in, and almost all of them just happen to look messy. That's a state of high entropy.
So, and this is the really crucial insight. The second law of thermodynamics, the one that says entropy always increases, it's not some deep directional force of nature. It's just statistics. It's just probability. Entropy increases for the same reason that if you shuffle a deck of cards, you're more likely to get a random mess than a perfect sequence. The arrow of time is really just the universe drifting towards the most probable state.
Okay, but wait. That just pushes the mystery one step further back, doesn't it? If messy, high-entropy states are so overwhelmingly probable, why wasn't our universe just born that way? Why on earth did it start in such a special, incredibly orderly, super low entropy state in the first place?
And here's where things get really wild. Because in that box of gas, a smooth, uniform state is messy, right? It's high entropy. But when you add gravity into the mix, the whole thing flips on its head. For an entire universe governed by gravity, a smooth, uniform state is actually incredibly orderly. It's a state of very, very low entropy. Because what does gravity want to do? It wants to pull things together into clumps, into stars and galaxies. So you can think of the early universe as being like a perfectly smooth, tightly wound spring. All that matter and energy was spread out so evenly that its incredible gravitational potential was just sitting there, completely untapped. The entire history of the universe for the last 13.8 billion years has basically been the unwinding of that cosmic spring, as gravity pulls stuff together, creating all this amazing structure and increasing entropy every step of the way.
And where does most of that entropy actually end up? Well, check out this chart. It is absolutely staggering. The little bar on the left, that represents the entropy of all the regular matter in the entire known universe. The massive bar on the right, that's the entropy of just one supermassive black hole. It's not even a competition. Black holes are the universe's ultimate entropy dumps. They are the most disordered, chaotic things possible.
Now, I know this might all seem a bit abstract, gases and boxes, the Big Bang, but it connects to something we all deal with every single day: information. The next huge breakthrough in this story was the realization that entropy isn't just about heat and particles, it's about data. Information, it turns out, is physical.
And this is where it gets really, really cool. Back in the 1940s, a guy named Claude Shannon, who's basically the father of information theory, came up with a mathematical formula to measure the amount of missing information in a message. And to the absolute astonishment of pretty much every physicist on the planet, it was the exact same formula that Boltzmann had used for entropy decades earlier. They're the same idea. Boltzmann's entropy is just missing information about where particles are, and Shannon's entropy is missing information in a message.
This leads to a totally revolutionary idea from another physicist, Rolf Landauer. He showed that information isn't some abstract, ghostly thing. It is physically tied to the real world. And specifically, the simple act of erasing information, like deleting a single bit from your computer's memory, has a minimum unavoidable physical cost. It must release a tiny puff of heat, which in turn increases the total entropy of the universe.
This discovery finally solved a famous century-old paradox called Maxwell's demon. The idea was that a tiny, intelligent demon could sit at a gate between two boxes of gas and sort the fast molecules from the slow ones, which would decrease entropy and violate the second law. So what's the solution? Well, the demon has to remember which molecules are which, and its memory isn't infinite. Eventually, it has to start erasing old information to make room for new information. And that simple act of erasing, thanks to Landauer, generates just enough heat, just enough entropy to perfectly balance the books. The second law is saved.
So, let's bring all of this home, because this isn't just about weird physics paradoxes or cosmology. This is about why you and I can even have a coherent thought in the first place. It is quite literally about the price of reality itself.
The really crucial point to grasp is that we aren't abstract observers floating outside the universe looking in. We are physical systems within it. And every single time you see something or form a memory or even forget something, your brain is processing information. And as we just saw, processing information has a real, tangible thermodynamic cost. It requires energy, and it always generates entropy.
So let's just put it all together one last time. Here are the big takeaways from all this. First, the era of time we all experience isn't some fundamental law. It's a direct consequence of the Big Bang starting in a highly ordered, incredibly low entropy state. Second, that low entropy past is the necessary ingredient for complex things, like memories, and us, to even exist. And finally, our very ability to think, to remember, to build a coherent picture of reality is a thermodynamically expensive process, and it's paid for by the constant, relentless increase of entropy in the universe around us.
Which leaves us with one last, truly mind-bending thought. We always ask the question, why does time flow forward? But maybe, just maybe, that's the wrong way to look at it. Maybe that one-way flow of time, this constant, irreversible unwinding of the cosmic spring, is the very thing that makes a complex, information-processing thing like a memory or a brain possible in the first place. So, is the arrow of time simply the price we pay for being here to wonder about it?